Hello students, how are you doing? I hope you are doing well. Today I have come with a new video. I have picked questions from magnetic effects of current and related topics. These questions were asked in the second shift of 25th January 2023 JEE mains. So let us discuss them one by one. So here comes the first question. For a moving coil galvanometer, the deflection in the coil is 0.05 radian when a current of 10 milliampere is passed through it. If the torsional constant of suspension wire is this, the magnetic field is this, and the number of turns, the area of each turn. This is based on the basic principle of a galvanometer, moving coil galvanometer. As you know, that when current is made to pass through a galvanometer, basically the current is made to flow through the coil within the galvanometer and it starts behaving as a magnet. Okay, it starts behaving as a magnet and there's a permanent magnetic field inside the galvanometer. So immediately it starts experiencing a torque, thereby twisting the suspension wire, the wire through which the coil has been suspended. So because of a twist, there will be a restoring torque within the suspension wire. So when the restoring torque within the suspension wire becomes equal and opposite to the deflecting torque due to the magnetic field, then the coil stays at rest. Now deflecting torque should be equal to the restoring torque. Finally, when the coil comes to equilibrium. So deflecting torque is vector m cross vector v, whereas this one is k into theta, restoring torque, where theta is the angle of deflection. Now here, remember that M and B, they are always at right angles to each other. It is designed in such a way that they are always at right angles to each other. So you can write M is sine 90 degrees, sine 90 degrees for. So M is A N I. A is the area of the coil, N is the number of turns, so that A into N is the total area, I being the current, you have this formula. So let us substitute the values. The area we have to find, number of turns is given as 200, current is 10 milliampere. So 10 milli converted into, replace the milli by SI prefix 10 power minus 3. Magnetic field is given as 0.01. So 0.01 I can write it as 1 by 100. Torsional constant is 4 into 10 to the power minus 5 Newton meter per radian, and theta is the angle of deflection. Angle of deflection is 5 by 100. So I have substituted all the quantities in SI unit and I expect the answer in SI unit. So SI unit of area is meter square. So we'll be getting the answer in meter square. Let us see. Uh, Here 100 gets cancelled both sides, 1000 gets cancelled here. 2 twos are. So we have area as 10 to the power minus 4 meters square. Since this is 10 power minus 2 whole square, so I can write this as 10 to the power minus 2 meter whole square, which is 1 centimeter whole square. So 1 centimeter square is the correct answer. I hope that is clear. Then moving on to the next question. A wire of length 1 meter moving with velocity at right angles to a magnetic field of 2 Tesla. This very simple question, students. Suppose B is the magnetic field here and L is the length of the wire and V is the velocity with which it is moving. Then the induced EMF is given by the scalar triple product of B, V and L. Scalar triple product. We have to treat the length as a vector quantity here because B and V are already vectors. Length should also be treated as a vector, so it becomes, you can extract the scalar triple product. If they are at right angles to each other, if B is perpendicular to V, which is also perpendicular to L, then the scalar triple product will be simply equal to the product of their values. Product of their values. So in this situation, you can apply this formula. So B is how much? B is magnetic field is 2 Tesla. So 2 speed is 8 meters per second and length is 1. So 16 volt is the answer. So then moving on to the next question. Question number 19. Two long parallel wires carrying currents this much and this much in opposite directions are placed at a distance of 7 cm from each other. A point P is at equidistant from both the wires such that the lines joining the point P to the wires are perpendicular to each other. The magnitude of magnetic field. So first of all, students, you have to know the formula for magnetic field due to a long current carrying wire. Here, long means infinitely long. Simply long would mean infinitely long. So for an infinitely long wire at a distance A, the magnetic field is given by mu 0 by 2 pi A into I. This is the formula. Okay. Here direction will be along the inward normal to the plane of the board. Okay. Then in this situation, let us take the top view. So as per the top view, I'll have this two long parallel wires carrying currents this and this in opposite direction. I'll take suppose 8 ampere current I'll take in this direction down and 15 ampere current I'll be taking up. Okay, they are placed at a distance of 7 cm. So this distance is 7 centimeters. This is the top view, students. Point P is at equidistant from both the wires such that the lines joining the point to the wires are perpendicular. So that means these are the lines joining the point with the wires and they are equidistant. That means these two are same and they are at right angles. So basically this is a right angled isosceles triangle. Right angled isosceles triangle. So each of the distances will be 7 cos 45 degree or 7 sin 45 degree. Anyway you can take 7 by root 2 cm each. Distance of the point from each of the wires. I hope that is clear. Now coming to the direction, you can see that due to this wire, I have taken this as I1 and this as I2. So due to this wire, it is going inside. So if you apply the proper rule, then it will be like this. The magnetic field will be in this direction. You have to apply the right hand thumb rule. Stretch your thumb in the direction of current. Let your remaining four fingers curl as usual. Use the right hand, students. So when you stretch your thumb in the direction of current, the remaining four fingers curl in the sense of magnetic field. That's how you derive the direction. And for this, it will be like this, in this direction. So you can see B1 and B2 are at right angles to each other. So resultant field, that is net field, can be obtained by applying the Pythagoras theorem. When two vectors are at right angles to each other, you know how to calculate the net. Okay. So here we have to let us calculate B1 and B2 separately and then we'll check what we can do. So B1 will be mu 0 by 4 pi. Mu 0 by 2 times of mu 0 by 4 pi, 2 times of 10 power minus 5. So this is 10 per 10 to the power mu 0 by 4 pi is 10 power minus 7. So 2 into 10 power minus 7 into I by A. I is 8 ampere and distance is 7 by root 2 centimeter to be converted into meter. Similarly, B2 will be again 2 into 10 to the power minus 7 into 15 upon 7 by 2 into 10 to the power minus 2. So this gives you 2 root 2 by 7 into 8 into 10 to the power minus 5 Tesla, and this will be 8 remains here. Okay, this will be 15 into 2 root 2 upon 7 into 10 to the power minus 5 Tesla. So when you substitute here, you get the net field. Whatever can be taken common, just take them common. So 2 root 2 by 7 into 10 power minus 5 can be taken common. You have 8 square plus 15 square root of this. So this will be 2 root 2 is 1.4 given in the question. This is 7, 10 to the power minus 5. This will be 17. You can calculate this. So cancelling 7 into 0.2, so I can write 2 to the 4, 4 into 17 is 68 into 10 to the power minus 6. Okay. 0.2 has been written as 2 into 10 power minus 1. That 10 power minus 1 and 10 power minus 5 has become 10 power minus 6. 2 to the 4, 4 into 17 is 68. So 68 into 10 power minus 6. So 68 is the correct answer. Moving on to the next question. We have a match the type of a question. You see, list 1 has certain fundamental electrodynamics laws related to electrodynamics, whereas list 2 has their corresponding formula, mathematical formula. Now, Gauss law in electrostatics. Gauss law states that the total electric flux through a Gaussian surface is charge enclosed divided by epsilon 0, and this electric flux is what? Total electric flux around the closed surface will be this. So A should be mapped to 4. A should be mapped to 4. So this is the correct answer, but still we'll explore other options also. I mean other things. So Faraday's law. Now Faraday's law is basically based on this. Now Faraday's law states that the induced EMF is what? The line integral of vector E dot dl, that is electric field dot dl, is the induced EMF, is equal to the negative of rate of change of magnetic flux. So this is Faraday's second law. Gauss law in magnetism is this: total magnetic flux through any Gaussian surface is equal to 0, because magnetic field lines are always closed lines. So corresponding to every line which comes out of the surface, there has to be one line which enters the surface. Okay, so that is why total flux width has to be 0. So C should be mapped to 2. Then finally, Ampere Maxwell law. This is Ampere Maxwell law, you all know this. Okay, so that's all in this video. Thank you so much.